So now we're going to take things up a notch and consider nested quantifiers. So expressions that involve multiple different quantifiers. This is contained in Rosen section 1.5. And basically what we want to do is make sense of expressions that look like the following. So I want to mix in multiple different quantifiers. So here I have a propositional function that contains two variables, x and y, and I have two universal quantifiers. Here I have a universal and an existential. Here I have a universal and existential, but in a different order. And here I have two existentials. So we want to really understand what's going on when we have multiple different nested quantifiers like this. And it's easiest to be able to look at a concrete example to be able to understand these things. So let's go ahead and from here on out consider q of x and y to be my proposition x plus y equals 1 right here. So that's my propositional function right here. With domain all real numbers. So let's go ahead and go one by one and see whether or not these statements are true. So let's go ahead and consider first for every x, for every y, q of x, y. It's easiest to understand this if we were to translate this back into English. So what this says is for all real numbers x, for all real numbers y, and then I take my propositional function right here, x plus y equals 1. And this, you can tell probably right off the bat, is false. So this thing is false because I have a simple counterexample. So if you let x equals 1 and y equals 2, then here an example of a couple of variables that are in the domain that q of 1 and 2, well, that's going to be 2 plus 1, that's a 3. 3 does not equal 1. Sorry, that's false. So there we go. This particular nested quantifier right here, this complicated expression, is false, because it's claiming that for all x and all y's, x plus y equals 1. Let's go ahead and move on to the next one and consider for every x there exists a y such that q of x and y. And again, to be able to understand this, I'm going to translate it back into English. So this is telling me for all real numbers x, there exists a y such that x plus y equals 1. Okay, is this a true statement or not? For all real numbers x, so I have to start with an arbitrary real number x, there exists a y, so then I have to go searching for a y that satisfies x plus y equals 1. Well, yeah, I could do this, right? So if you give me some arbitrary x right here, I can go ahead and find you a y such that x plus y equals 1. Indeed, let's let y equal 1 minus x. And if I were to do that and then take a look at the value of q of x and y, well, that's going to be q of x and 1 minus x. If I go back to my definition of q, that would be logically equivalent to saying x plus 1 minus x equals 1. And yeah, this thing simplifies down to 1 equals 1. And that right there is a true statement. So given an arbitrary x, I have found you a y that makes my propositional function true. Therefore, this nested quantifiers right here, this is true. So this thing right here is logically equivalent to true. On the flip side, let's go ahead and flip the existential and universal quantifier and consider there exists an x such that for every y, q of x and y. So again, translating it back into English, there is a real number x such that for all y, x plus y equals 1. And if we think about this for just a little bit, we can see, no, this is not the case. There is a real number x such that for all y, x plus y equals 1? No, that's not going to work. Because if you were to find me some value, let's say x equals a, then I can go ahead and show you that for every y, q of x and y is not going to work. So assume that you had some sort of value that you thought made this thing true right here. Well then, q of x and y, in this particular instance, you said you found that magical value, there exists an x, so you called that thing a, and I'm letting y be 2 minus a right here. Then this thing is going to be logically equivalent to the statement a plus 2 minus a equals 1. Ooh, uh-oh. This is logically equivalent to 2 equals 1. And that thing here is false. So you have proposed for me a value of a real number such that for all y, x plus y equals 1. Sorry, it is not true that for every y, that particular value of x plus that y is going to be equal to 1 because I just gave you a counterexample right there. So this particular one is false. So the big takeaway from this particular part is that order matters. So let's put that big in red. Order matters a whole lot for your quantifiers. We saw that if we switched this universal and the existential quantifiers right here, I went from a true statement to a false statement over here. So order definitely matters when looking at these nested quantifiers. And I'm going to leave it to you as an exercise to show that if I use two existential quantifiers right here, this thing is a true statement. So whenever you see nested quantifiers, it is oftentimes helpful to translate them back into English sentences. And then after we've translated it into English sentences, we can sit back and we can think, well, what is this bunch of symbols actually claiming? And so for example here, I found that what it was claiming was that, oh, you give me an x and I can go find a y that satisfies this equation. And here I found that it was saying, well, if there's some magical x that makes this equation true for all y, no, that's not going to work. So translating it back into English will help you to be able to understand and unravel what these nested quantifiers are meaning.